Force of gravity. Okay, very easy one. What's the equation for force of gravity? mg, right? Fg equals mg. So Fg equals, I like to call it mvg, acceleration due to gravity. Okay, we all know how that one works. Pretty simple. Next up we have, and this is just a review because we've been away for a week, right? Right? Then we have force normal. This is kind of the counterpart to force gravity. Okay, what does force normal mean? This means that any object that's being pressed along a surface, okay, whether it's due to gravity or not, or it could be any surface that's vertical or sloping, right, will oppose that object's pressing on that surface. Right? So it's always perpendicular to the surface, and it's always going in the opposite direction. This is kind of an extension of Newton's third law. Right? Is there an equation for this? Not specifically, no. Okay. Oftentimes it is just going to be mg, but you have to take into consideration that maybe you're on a sloped surface, and also you might have something else that's pressing against it, right? We have a table that has an Fn, but if I push down on the table, the Fn is going to increase, right? If I pull up on it with a rope, then the Fn will actually decrease. So you really have to draw your diagrams first before coming to conclusions. Speaking of ropes, we also finally had a force tension. Okay, so force tension is any pulling motion that's performed on an object, usually done with ropes or chains or strings, and we label this one as Ft. Okay, you'll see this one in a lot of situations. As usual, it cannot push on an object. The rope itself is massless, so we're not going to pretend like the rope has a mass and is involved with like internal forces. Okay. And is there an equation for this one? Also not really. Okay. So if we want to calculate Ft, we have to use F equals ma. Right. With both force normal and Ft, we have to use force or F equals ma. And then pour out the entire equation, which may be a little bit complicated, to isolate algebraically this Ft. Okay? So those are those three. And then finally, with last week, we did the free body diagrams, right? So as long as you were here, we did a big MIT-style video and worksheet, which I just gave back to you. I was pretty easy on the worksheets again because force friction, we did not get into too much detail about it. Okay? So I think it's not fair to judge it based on that. And this is basically a process of how we can start drawing a force body diagram or free body diagram. You guys remember? Right? They're fairly easy. And the reason we have this free body diagrams is so that we can create our equations. Right? We have all our forces in the x directions very clearly displayed. We have all of our forces in the y directions clearly displayed, so then we can make our fx equals max equations, and our total fy equals may equations, and then solve for whatever variable we're looking for. Okay, so that's the purpose of our FBDs. And these are some examples that I give to other students. I think we can skip it for this school. All right, any questions about review of the previous stuff? Okay. All right, well, our last force, possibly the slightly most complicated. They're just doing that for technical purposes.
That is
I don't want you to
dynamic friction. That is stationary friction.
Okay, well, let's slow down. Not necessarily dynamic. Right? Are these moving?
Oh,
Not necessarily. We don't really know.
we assume they're moving.
Yeah. But regardless of whether it's dynamic or static, I mean, it's still pointing in the same direction. Okay, so now
we will only talk about the direction of the friction.
Yeah, now this is just the introduction. Just the introduction. And again, if you're pressing a box along the wall, for example, if you're pressing just a little bit, it's going to be easy for it to fall down. Notice that. But if you press that box on the wall really strongly, then the force of friction will be higher and will be sufficient enough to keep the box in place. So that's another observation that I want you to make. If you press that box really hard, which of these forces is affected? Normal force. Okay? If I push it just a little bit, the Fn is very small. It slides down. If I press on this box really strongly, the Fn is going to be strong right back at me, and it actually stays in place.
So it isn't the perpendicular to each other that they cannot have.
You mean Fn doesn't have an effect on Fr? That's force friction? Okay, well again, I'm trying to develop a relationship here, so I didn't give you the equation yet. But what you do have to recall is that, yeah, Sam's right, force friction is always perpendicular to force normal, which is another way of saying that force friction is always parallel to the surface. Okay, so it's actually unnecessary information. Oops. What is the other bit of information, conceptual, that we have to remember about force friction? Is that it really, as David said earlier, I guess somebody's been reading ahead in the book, there are two kinds of force friction, okay? It'll come in two forms depending on whether your object is stuck at rest or if it's already in motion, okay? So in this case, let's say we have a trash can. If we push on this trash can, it's not necessarily going to move. Right? The force friction is pushing back on us. It's very stubborn. It's not going to move. But there's still friction. Right? So we're pushing on it. It's pushing back. These are equal. Right? The Fs means force friction static. Static means staying in place. Okay? That is a different kind of force friction than if that trash can was already moving. Okay? Maybe you've done this with like moving the couch. Right? To get couch, it's really hard to get the couch to start moving, but once it's already moving, then it's a little bit easier. Right? So that's why, what does the K stand for then? Yes? What? FFK. Kinetic. Right. Kinetic force. Yeah, kinetic. So kinetic generally means moving. Right? That's why our previous subject, motion, they usually call it kinematics.
But you see, when it is in the motion situation, the friction of the kinetics is less than the friction of the stationary situation.
That looks like the case. That looks like that's the case, huh?
That's the case. I mean, that's the key point here.
I mean, that's the situation.
So,
still working on the TOEFL score.
it is correct. It is correct that the
They're not lying. You're not lying. What I just say? I said if you're pushing a couch, let's say you're helping your uncle push your couch. Starting to push the couch is really hard. There's a lot of opposing friction. But once you get moving, right, it's a little bit easier.
Okay.
And that's how scientists kind of determine, like, okay, this FFK is probably smaller than our FFS.
Have they proved this?
Yes, they
I
have.
still remember there's a SAT the article of model of friction.
Yeah, they have hypothesis of the model of friction.
I don't think there's any situation in which the FFK would be greater than FFS.
Okay.
So let me stick these in our box here. So now you guys know, right? So we have force friction, and this can split to FFS or force friction. Yeah, fourth and final force. Oh, this is a good diagram. So a little animation here, what's going on here. So just to distinguish between force static and force kinetic friction, okay? I failed to mention one of the key points about force static or friction static. And this animation will kind of show you. So we have a B pushing on this box. It's trying to push, and then it gets going.
Strong B.
Very strong B.
Yeah, your brother.
Diligence. So initially, when the block is not yet moving, what kind of force is that?
The last and friction equal to friction.
Yeah, equal to friction.
No, before it's moving.
Yeah, before it's
Oh yeah, it's equal to
There's forces, it's not moving yet because